Okay, so welcome to another lecture, and today's lecture is gonna be about proving methodology. What do I mean when I say proving methodology? It's basically using logic and certain given statements or mathematical propositions, as we have learned, and find if they are true or false. And evaluating statements, basically composite statements using implications and statements or statements, and basically compositions of all those connectors and trying to find certain proofs. Now, these proofs can also include some sort of well, not all proofs are mathematical statements. There are other sorts of proofs that are more complicated, and we will learn more complicated and more structured, well thought out strategies that really will require some amazing thinking. So let's just get into it. Right now, we have something which is called a direct proof or a direct explanation of whatever we have to prove or check for here. So here we have to check what all of these statements are true. So if I just pick a different color, maybe pink, and if I see we have an A implies C, where A is any x between 5 over 2 and 1 over 2. So if I draw these out on a number line, it's gonna be something like 1/2 and 5 over 2, and all of the numbers, all of the possible x's for x belongs to R are going to be here. So x belonging to half to 5 over 2. Notice the open intervals here. So I'll just put open brackets. So this is what A says, right? And similarly, what we have to evaluate is A implies C, if this is true or not. So if I just erase this now, right. Uh, let's get into it. So what does A imply C mean? It means that if A is true and C is false, that's the only case it's going to be false, right? So if A is true and C is false, so in that case, we will have something like true implies false, which will make this statement false, right? Otherwise, what we can do is check for all cases where we can find these to be true, right? So if you need to prove something false, you will have to come up with a counterexample if you don't have the theory for it. So let's just see what that will look like for us. So we have A, which says that x belongs to 1/2 to 5 over 2, that interval for x belonging to real numbers. So all real numbers between this interval and this interval, between these two endpoints, are going to be included in A, and C is x squared equal 1, the solutions to which are -1 and a +1, right? And this is for x belonging to R. So x will be plus or minus 1, and here x will be these values. Now I can already see a counterexample for A implies C. So here does x, if I take some value for x, right? Let's take an example. If I take x equal 1, this will show me that x belongs in A. Why? Because 1 is included in this set from 1/2 all the way up to 5 over 2. So this point, a 1x here will always be in this interval. And because x belongs to A, I can say that x belongs to A is true. And x will belong to C as well, because we see that -1 and +1 are the two values that are included here, right? So if I need to find a counterexample, I will need to, because this doesn't prove anything. This is one example of it being true. We need to make it true for all possible values of x. And all possible values of x are given here, right? So I need to check for all possible values for x. But if I find just one value in which this fails, that is going to be my counterexample, right? So for a counterexample, it's exactly the opposite. We just need one value where this A implies C fails, right? So for a counterexample, let's take the value x equals, let's say 3. Will that work? I don't think so. Let's just see what happens, right? So this thing is 2.5, right? So I'll have to extend my number line a little bit, and let's see what happens here. So x belongs to A and x belongs to C. This thing is false because it's not in this interval from 0.5 to 2.5, this colored thick pink region here, and hence this is false. And this is also false as C only allows x to be -1 and +1, right? So if I want to find a counterexample, I need to find when this implication is going to be false. And when do we know an implication is false? An implication is false when true implies false, right? I want A to be true and C to be false. So when is A true? A is true on any interval between half, any value between half and 5/2, which is the same as saying 0.5 and 2.5. So any number between these satisfies these conditions. But what about C? Well, C only allows -1 and +1. So any value that is between this interval, something like, I don't know, maybe 0.7. 0.7. So let's take x equals 0.7. X equals 0.7 makes x belongs to A true. Why? Because, well, it satisfies the condition. And like we know that 0.7 is between 1/2 and 5/2, right? And just because of that, we can say that x belongs to A is true. X belongs to C, on the other hand, is going to be false because only -1 and +1 are allowed. So there we have a counterexample where A implies C is false. So that's how we can prove that this statement here is going to be false. Always, this is just one small thing to keep in mind. Whenever you're proving true, giving an example is pointless. Because, okay, it's not actually bad to give an example, but when you're proving something to be true, you're just putting one instance of when it is true. It is obviously going to be true for over a really large interval of values. Like in this case, we had x belongs to R, and it was like a large value, right? And in that case, we cannot justify it being a true statement just because it has one example that satisfies it. Counterexample, on the other hand, is an easier way to prove false. So when you are proving something to be false, always try to find a counterexample because that directly proves that that statement is false, because there exists one such value where it does not hold. So if we just go up, we know that this is false. Perfect. Next question. We have A and B. Let's just mark it right here. A and B implies C. Let's go down and let's just write it up. So we have A and B implies C. Let's recall what A, B, and C are. A is x belonging to half to 5/2. B says that x belongs to all integers, and C says that x squared equals 1, right? So if it says that A and B, it means that A and B are true. So when is A true? A is true when x is in the interval 1/2 to 5/2. And when is B true? B is true when x belongs to integers. When is A and B true? So A and B refers to the point when both of them are true. So we want x to be an integer as well as in half 2 over 5 over 2. So that's just going to be the set of values 1 and 2, right? Perfect. So we wanted to imply C. And what is C in our case? C is x squared equal 1. And because x belongs to R, x belongs to all real numbers. Here in the question it said that itself. I'm not building this up, I swear. And let's just go back down. As it's all real numbers, we know that C can be only plus or minus 1. So plus 1 comma minus 1, right? And as we can see directly that there is a value in A and B that is not in C, right? And that can be our counterexample. So this part of the implication, the hypothesis of the implication will be true, and that will imply to something which is false. So we have a counter example for x equal 2. And because 2 belongs into this set and does not belong here, we can easily say that A and B implies C is false. Perfect. So we have this thing as false as well. Next, if we say this is something really a little complicated now. Let's try it out anyway. So we have, let's write it down. So let's hit it. Okay, I'm excited. Let's go. So the third statement says, why is this so thin? Okay, perfect. Right. Amazing. So D implies A and B and negation of C. Now, if I want to write down all of these again, A is just saying that x belongs to 1/2 to 5 over 2. B is saying that x belongs to all integers. C says that for every x in C, x squared is equal to 1. And D just says that x is equal to 2. Now, okay, so this is basically saying that if x belongs to D, remember this is an implication, so it's always going to be an if-then type of statement, right? So it's going to be if D, if D, then A and B and negation of D and negation of C works, right? So if I say that if x belongs to D, then A and B and negation of C will hold. So x should belong to this thing as well, right? So what is the set D here? D is the set containing 2, and this makes things easier because we only have to check for one example and we can easily find a counterexample. So true implying false. We just have to see if this entire ugly set contains the number 2, right? So it's if it contains the number 2, it's going to be true here and then true here, which will make this statement true. And if this is false, it's going to be false. And if we have to check vacuously, we can do that too. So if this becomes false for some reason, which it shouldn't, but well, let's see. So what do we have here? A is gonna be anything between, let's just draw a number line at this point, right? So we know that from 1/2 to 5 over 2, what all can we use here? We need A. We already have A. This is all of A. This is currently my set, right? This is what I have to work with. If it says A and B, so I need this interval and I need it to be an integer. That means that it wants me to take all the integers values in this interval. So I will have some 1 here and I will have 2 here. So currently my set looks something like that. From the interval 1/2 to 5/2, I have to take out all the integer values and write them in a set, right? So what do we have now? Next we have C, x squared equal 1. So it says that x equal +1 or -1. So let's just see. X equal 1, that's x equal 1 here. Let me scroll down a little bit. Yeah, that this point is x equal 1, and x equal -1 will be somewhere here. We don't care about that because we know we need a, right? We need a to be true because there's an and statement in the middle, right? It stays and. That means all of them should be true in order for the whole statement to be true, right? So if a and b and negation c is true, then we need a as well. And a does not include -1, so we do not find this anything interesting or worth it. If it says that x equals 1, we're supposed to take negation of c, right? So x is not equal to 1. So we can't allow this R set A intersection B. Okay, R set A intersection B was what? It was the set from 1 comma 2, right? From the previous thing. Negation of C was the set was what? If if C, we have C, which is equal to x squared equal 1, and this basically is the same as saying that x equals plus minus 1, then negation of c is going to be x is not equal to plus minus 1, right? And if I take the and of this and this, that is, if I take an and statement, if I take both of them together, then I'm supposed to say that a and b and negation of c will give me what? It'll give me this set, but 1 and -1 are not allowed. That means it's just going to be this, right? And the only example of D is the set containing 2. So let's just write down what we have. It says that if x belongs to D, then x belongs to bracket A intersection B intersection negation of C, right? And that's what all of this ugly math we just did is just saying, right? So if x belongs to D, it means that x can be in the set D, and the set D is just the value 2. That means that if x is equal to 2, then 2 belongs to the set 2, which is true. So we just proved directly that true implies true will always give us a true statement. Perfect. What about the conditions where true implies false or false implies false or false implies true? What are we going to do to those statements? Well, those statements, all of those cases are inconsequential. Why? Well, if you really think about it, we are given very specific, very specific cases here, right? We are given these statements, and based on these statements, we found out the values to be specific, right? If we don't know what our statement is, if we don't know what arbitrary statement we have been given, only then we need to consider all cases. In this, we can eliminate these cases. We can eliminate 1, 2, 3, these last 3 cases, because true will never imply false. When? When will it never imply false? When D implies A intersection B intersection negation of C. And the same goes for even this and this, because like if X belongs to D, then this happens. It always will. And hence, this last part is always true. A very good question, though. I liked it. So, next we have some proof strategies, which I think I'll make a separate video about. And I'll see you in the next one. Peace.